Okay, so we are going to pick up on the preparation of alkenes. So alkenes are interesting because, in a sense, they are intermediate between saturated compounds and alkynes. So, for example, I can imagine that we could generate an alkene either by loss of HX, so elimination of HX from a saturate, or we can generate the alkene by partial hydrogenation of an alkyne. And so philosophically then, that gives us a sense of the approaches we will take in preparing alkenes. So the two broad approaches would be elimination of some HX, right, 1,2 elimination from a saturated compound. And then the second motif will be partial hydrogenation of an alkyne. And both of those come with some peculiar nuances we'll try to develop as the lecture goes on. So let's start with the first one, which is elimination. So we're going to prepare alkynes. Again, this is preparation of alkynes, preparation of alkenes. So preparation of alkenes. And method one, find a marker that works properly. Right, and so one would be by elimination. And we're going to eliminate two different species. So the first would be dehydrohalogenation. So this is the elimination of HBr or HCl and so on. And I'm not going to spend much time on this because we covered it at great length when we looked at E1 and E2 reactions. So I'll just mention that we treat this with some base, typically at elevated temperatures. The reaction can go E1 or E2, and that will generate your alkenes. And in the particular case, you will generate the transalkene, the cisalkene, and the 1-alkene. And all of those factors that we talked about in terms of Seytz's rule, the size of the base, and all that kind of stuff, that will apply. And the various factors that push the reaction along the unimolecular pathway and the bimolecular pathway, those apply as well. So I'm not going to get into that in any detail because that was covered extensively when we looked at E1 and E2 reactions. What is new will be the dehydration reaction. And so the second method of elimination is by dehydration. And this is a little bit more involved. So dehydration. One of the ways in which you can look at this is that if you take a primary alcohol, for example, ethanol, you take a secondary alcohol, right? 2-propanol or isopropanol, and you take a tertiary alcohol, like say T-butanol. If I treat this with conc sulfuric acid at about 180 degrees Celsius, I'll generate the corresponding alkene. Functionally, what I did is I'm removing HOH, so I'm losing H2O to generate the product. I can treat this with conc sulfuric acid, probably at about 60 degrees or so, and that's going to generate the corresponding alkene. And in a similar way, if I treat this with just really dill sulfuric acid and I warm it, that will generate the corresponding alkene as well. But what you notice is not only that we've dehydrated the alcohol, so we've lost H2O, but that the conditions under which dehydration occurs gets less and less severe. So we're using really forcing conditions, conc acid at really elevated temperatures for the primary alcohol. It gets somewhat easier for the secondary alcohol, right, much lower temperatures. And I really don't even need conc acid for the tertiary alcohol. It dehydrates very, very easily. And whenever we see a pattern in which a reaction gets more facile, as we go from a primary substrate to a secondary substrate to a tertiary substrate, what that strongly implies is that there's a carbocation intermediacy. So we're generating carbocations. Because as you remember, tertiary carbocations are pretty stable, so they're readily accessible. Then secondary carbocations are modestly stable, so I can make those. So whenever reaction gets progressively easier as we go primary to secondary to tertiary, that is a strong indicator that the reaction is generating a carbocation in the rate determining step, right, for the reaction. So let's give a look at the actual mechanisms for these reactions and see if our hypothesis for the generation of a carbocation is actually valid. So the way in which these reactions go, and I'll pick the secondary alcohol, is the alcohol in the presence of the acid. And of course, sulfuric acid, if you remember your Gen Chem, looks like that. Acids do one thing and one thing only, they protonate. And proton transfer is the fastest reaction in organic chemistry. And as a result, it's the first reaction in organic chemistry. So acids protonate. Who do they protonate? They protonate bases. What makes me a base? Having either a lone pair of electrons or a pi pair. So really then, the first event is that the alcohol acts as a base and deprotonates the acid. There's a proton transfer. And since it's an acid-base reaction, I'm going to write an equilibrium arrow that will generate the protonated alcohol. There will be a positive charge on the O, and we call this species an oxonium ion. And just to remind you, yum ion means that you're positive, and onium ion means that you're hypervalent and positive, that your valence is one more than what you predict from the periodic table. And ox indicates which atom is hypervalent and positive. So the oxygen has 3 bonds, so it's hypervalent. It has a positive charge, so that's an oxonium ion. We're going to, of course, lose bisulfate in this reaction. So HSO4 minus. The oxonium ion has a labile bond. That CO bond is pretty labile. And so what happens is we're going to lose, we'll go this way, we're going to lose water. So water comes off. And the loss of water is also an equilibrium. The loss of water from a positively charged species is an equilibrium because, as you can imagine, the products of this reaction are a secondary carbocation and a water molecule. Well, water is also a modest nucleophile. So if I have exposed a carbocation to a nucleophile, then the water is going to attack the carbocation and regenerate the oxonium ion. So this event is an equilibrium. In fact, for much of the introductory organic sequence, organic 1 and organic 2, there are very few reactions that you must know are equilibrium. And 2 of them are acid-base reactions. So whenever you draw a mechanism, you must draw an equilibrium arrow. And the loss of water from a positively charged species, right? Those are equilibrium reactions. So I make my secondary carbocation. And that species then reacts with water, which now functions as a base, pulls off the proton, and generates the corresponding product. So you make the corresponding alkene from the reaction. So the dehydration of the alcohol involves protonation of the alcohol to generate the oxonium ion intermediate, loss of water to generate the carbocation, and this step, of course, is the rate determining step, and then a fairly facile deprotonation of the carbocation to generate the corresponding alkene. And obviously, if we're making a secondary carbocation, this is modestly easy. If it's a tertiary carbocation, it will be very easy, right? So you need less forcing conditions. But of course, we know we can't make primary carbocations. So the question arises, how then do primary alcohols dehydrate? What's the mechanism for that reaction? Now, I will point out, if I look at the reaction from this perspective, I can call that, in a sense, an E1 type reaction, right? So let's look at the primary alcohol. So let's see how ethanol dehydrates. Well, it starts off the same way. The alcohol is a base. It reacts with the acid, and that's going to generate the corresponding oxonium ion. The difference is we can't simply lose water as we did in the previous case, because that's going to generate the primary carbocation. That's illegal. That's way too energetic a species to access. So instead, what's going to happen is we're going to end up with the reaction undergoing an E2 type elimination. So I'm going to have a species, perhaps another water molecule, come in, suck off the proton, and I have loss of H3O plus, and I'm going to lose H2O as well, and that's going to generate my corresponding alkene. So this is actually going to be an E2 mechanism because you want to circumvent the formation of the primary carbocation. It turns out that because the dehydration reactions, with the exception of ethanol as a primary alcohol, because they generate carbocations as part of the mechanism, it throws a slight monkey wrench in the chemistry. And here's an example. If I looked at, let's say, this compound, and I wanted to generate the corresponding alkene, let's say I wanted to make this compound. Well, this is a no-brainer, right? Here's my alpha carbon, the carbon bearing the halogen, or the heteroatom. Here is the beta carbon. And so I could make the argument very easily, well, all I need is a strong base, which will pull off the beta H, right? So a strong base to pull off the beta H. And so I'm going to use this under classic E2 conditions. So 3.5 molar, let's say, sodium methoxide in methanol, and I'm going to heat it. So let's just say we do reflux. And those are the classic E2 conditions that will generate the alkene. And of course, in a case like this, you know, there's going to be a conformational change. So the bromine ends up here. So I'm going to lose the H from this position. So this is the methoxide acting as the base, carrying out the E2 reaction and generating a product. But my point is, if I know where the halogen is, I need look no further than the adjacent carbon to see if I can get the E2 reaction, right? Get the E reaction. It turns out that if I took the companion alcohol, and my intent was to make this compound, if I said, well, here's where my OH is, and so I'm just going to look to the adjacent carbon to find my H, and then all I need to do then is to heat this with conch sulfuric acid. If I did that, this is not the alkene I'm going to get, right? And the reason is because this reaction generates carbocations, and carbocations, among many things, rearrange. They're very hot reactive species, and they tend to rearrange. So it turns out that the major product of this reaction is actually this one, right? The major product of that reaction is actually that compound. So clearly what we've done is we've rearranged the carbon skeleton, right? In my substrate, I had one carbon that had 3 methyl groups on it. That no longer exists in my product. And in fact, you can probably tell if I were to number my carbons, 1, 2, 3, 4, 5, 6, you can probably tell if I call this one, if I say this is carbon 1, and then this is 2, and this is 3, this might be, let's say, 4 and 5, then carbon 6, so one of these carbons, has actually moved over to carbon number 2. So we've rearranged the carbon skeleton. So in fact, if I were to describe this reaction or to define it, I would say it's a dehydration with rearrangement. If I were to classify the reaction, it's a dehydration with rearrangement. So we need to figure out exactly how this happens and why it happens. And if we understand how that happens and why, we might be able to find a way to convert this alcohol, for example, into that compound if we need to, which we can talk about in a second. So let's go ahead and look at this reaction in more detail and sort of figure out the mechanism for the conversion of this alcohol into the alkene. Well, if I treat it with the acid, again, the first step, and I'm just going to write the acid as HX, right? So sulfuric acid, let X be the bisulfate. The alcohol will deprotonate the acid. We're going to lose X minus, and that will generate the oxonium ion. The oxonium ion, again, water is a really great leaving group. So the oxonium ion is going to want to lose the water molecule, but it can't that simply because that will generate the impossible primary carbocation. So instead, what happens is one of the H's in a beta position migrates over, and what we get is a complete circumvention of the primary carbocation, and we end up with a secondary carbocation. So that process in which, suppose we're going to lose water, so this is a loss of water, we're going to lose the water molecule, but I also do what's called a hydride shift. So we can say either that's a hydride shift, and we'll talk about this in some more detail in a second. We can represent hydride shifts by curly line H, right? So when groups migrate from, or shift from one carbon to the adjacent carbon, that's called a shift or migration. And if it's an H that migrates, it's called a hydride shift. I'll explain why it's I in a second. But as we see later on, we can have alkyl group shift, we can have methyl group shifts, it can be a methide shift or an ethine shift and so on. Once we've gotten here, and in fact, why don't we talk a little bit about exactly what makes that process possible, and then we'll continue on the other part of it. So let's kind of figure out exactly how this hydride shift occurs. So if I were to draw a carbocation, let's pick a secondary carbocation, which is not quite the example I have here, but let's pick a secondary carbocation. So let's pick a secondary carbocation. Let's say that's an H in this position, and then I'm going to have a carbon here that might have an H. Yeah, let's say there's a methyl group here, and let's say I've got another set of H's in this position too. Let's make it let's say methyl and methyl. So I'm making a carbocation. Which is secondary, right? So I've got a methyl here, and then an isopropyl group in this position. But that I've generated a carbocation here, and it could have been formed by loss of bromide or loss of water or something, and that doesn't really matter. So this, of course, is planar, and there's a vacant p orbital. Now, the p orbital has some reach, so it's like an arm. And carbocations are functionally unstable species. What makes it unstable? Well, it's positively charged. And secondly, it doesn't have an octet. It's missing 2 electrons. So the arm of the p orbital is going to function as a thief. And it's going to reach over to an adjacent bond and steal 2 electrons. Well, how far can it go? And the answer is, well, the p orbital is a finite length. So it can lean over to this bond or to that bond. But it can't, for example, get to the bond in that position. So we're looking at a 1-2 bond theft, 1-2 bond theft. It can't go 1 bond, it can't go 3 bonds. So in fact, I'm going to diagram this in a slightly different way. Instead of drawing the CH bond as I've drawn it in this fashion, I could draw it to show the sp3 hybrid of the carbon and the s orbital of the hydrogen. And there are 2 electrons that are in that bond, right? Here's my H. I can do the same thing here. I've got the sp3 hybrid of my carbon, and I've got the H, and there are 2 electrons here. So what my p orbital is going to do, is essentially lean over and borrow, it's going to lean over and merge with those two electrons and steal them, and lean over, merge with these two electrons and steal them. So let's imagine it going, doesn't matter, to the right. So what will that look like? So somewhere in the middle, I'm going to end up with a structure in which the p orbital has leaned over and merged with the orbital of the CH bond, right? Of the sigma orbital of the CH bond. And there are still the two electrons in that position, and the entire entity has a positive charge. So the positive charge now is sort of delocalized over the system. You would also notice that what's begun to happen is that, see, as the p orbital leans over, it gets less p-like as it grabs onto those electrons. So this lobe has begun to shrink. And similarly, the sp3 hybrid has started to become less sp3-like and started to look more p-like, right? So this lobe is starting to get slightly larger. So in the middle, let's make this a little bit bigger. So somewhere in the transition state of that phenomenon, we have basically this carbon and that carbon having equal ownership, if you will, of those two electrons. Also, what is going to happen is that this side, which was trigonal planar, and that side, which is sp3 hybridized to tetrahedral, in this position, they're neither, right? So this is going to be halfway between trigonal planar and tetrahedral. So will this one. It'll be halfway between trigonal planar and tetrahedral. So if I were to try to hazard a diagram, it'll look something like this and that, this and that. So it's not quite flat, but it's not quite tetrahedral either. It's somewhere in the middle. And then eventually what would happen is the p orbital would abscond with the electrons completely. So I'd end up with a scenario now where we look something like this. So it becomes completely sp3 hybridized, and that folds all the way down. And this orbital develops completely into a p orbital, and we are trigonal planar. So what would happen is the p orbital leans over, grabs the two electrons, pulls them, and that leaves this carbon devoid of the electron it had invested in the bond, and hence it has a positive charge. So what's going to happen is that once we've generated the positive charge at this site, the p orbital immediately starts to sample the neighbors to see which electron pair it can access. So you can lean over, sample this electron pair and start pulling it. It'll lean over and sample that electron pair and start pulling it. But here's the issue. If I look at this one, if I were to lean over, now I'm a secondary carbocation, if I lean over and grab those two electrons and pull them over and deposit a positive charge here, well now this carbon becomes primary carbocation. That's not legal, or primary carbocations are exceedingly unstable. And so I would go from a secondary carbocation, modestly stable, to a primary one. That's not going to happen. So it's not as if the p orbital doesn't start to sample it. It does. It leans over and starts to pull it. But as it pulls it and this carbon starts developing a significant positive charge, it stops. So then the p orbital will lean over to the other side and start pulling those electrons. But you will notice that as you're pulling the electrons over, this carbon is actually going to become a tertiary carbocation, and that's pretty good. So I can do a hydride shift from the left and go from secondary to tertiary, secondary carbocation to tertiary carbocation. What I cannot do is go to the right and go from a secondary carbocation to a primary carbocation. So in general then, what rearrangements are allowed? And the answer is anything that does not involve primary carbocations. So I can go from secondary to secondary, that's just exchanging pawns in chess. I can go secondary to tertiary. I can go tertiary to tertiary. I can even on occasion go tertiary to secondary. I can never go to primary or from primary, right? I can't make primary carbocations. I'll just make a point here. The justification for going from a tertiary carbocation to another tertiary or tertiary to secondary is actually fairly straightforward. When you're tertiary, the charge is stuck on that single carbon. But as you start to rearrange, there is a period where the positive charge is delocalized over the site, right? And so you get some temporary reprieve by delocalizing the positive charge. The one other point I'll make is that the p orbital is not even vaguely interested in the atom. So for example, I've drawn this as the H is moving. The p orbital doesn't care, doesn't know or care who the carbon is bound to. All the p orbital wants is the lone pair, is the bond pair of electrons. So it wants to get those two electrons. It doesn't care who is attached on the other end. What's also interesting is that, and we'll talk about this in a second, when the p orbital grabs electrons and pulls it, electrons move at the speed of light. Atoms are much slower. So really what happens is that the p orbital leans over, grabs the electrons and pulls, and then the atom here lags behind. Now, if you notice then, when this H moves, it really moves as two electrons followed closely by H+, because the p orbital leans over, grabs electrons and yanks them, and then the H follows behind. So really, in a sense, we're moving two electrons and an H+ all together. Well, that's really H-. That really is hydride, which is why these are called hydride shifts. Now, I could have said, for example, let's say the group on this side was T-butyl. Well then, instead of an H, I'll have a methyl group here. The p orbital will do exactly the same thing. It will lean over, grab the two electrons and yank them, and then the methyl electrophilic species will just follow behind it. I would call that a methide shift, right? That would be a methide shift. Or some people say methanide shift, right? They're called methide or methanide shifts. And they are represented by a curly line methyl, the same way the hydride shift is represented as curly line H. So that's the symbol we use to indicate that there is a shift, whether it's an alkenide shift or a hydride shift. And those are the only two groups, at least at this level, that undergo shifts. So if we go back to this structure, so in this case we had a hydride shift occurring in tandem with the water loss, because we can't make a primary carbocation. So the water can't just leave on its own. It requires assistance from the two electrons in the CH bond. There's a push-pull, but that then leaves a hole, a positive charge on the secondary site. Well, that's the secondary carbocation. The secondary carbocation rearranges by a methide shift, which we just talked about, and that's going to generate a tertiary carbocation. Right? I'll have a positive charge on that side. And then, in the final step of the reaction, a base, which in this case will be water, the water molecule I lost here, the water molecule comes in, acts as a base, sucks off, acts as a base, and I can do this in a couple of ways. I can suck off this proton, and that's going to generate this alkene. That's one option. But this carbocation can give a second option. So I'm gonna. There's an H in this carbon, and so there are two methyls and an H. I'm gonna slightly redraw this so that the methyls are down and the H is up. So the water molecule can also attack in this fashion, generate this alkene. And in both cases, I'm going to lose H3O+. And obviously, if the same carbocation is confronted with the choices of making a di-substituted alkene or a tetrasubstituted alkene, it's a no-brainer. It's going to make the tetra one. Okay? And how do I know that? Well, we talked about the Hammond-Leffler postulate recently. So I'm starting from the same carbocation, which is this one, and I'm going to generate the corresponding alkene. If the alkene is disubstituted, then I'm going to end up with a species that has that's less stable. Well, actually, this is slightly off. I'm going to end up with a species so starting with the same carbocation. I'm going to end up with an alkene that is at this energy level or at this energy level. And it really is a no-brainer. The system is going to try to generate the more stable product. Right? The transition state will be lower for the more stable product. So by and large then, we favor the more stable product. And this would be the major product. So in terms of yield, this would be major. This would be intermediate. And if you look, for example, from the secondary carbocation, it is possible that the secondary carbocation before the methyl shift occurs, I could have had a water molecule come in and deprotonate and give rise to this alkene. Right? So I could actually get that reaction to occur as well. So I'll lose H3O plus and generate that alkene. But in terms of yield, this is the minor product. And let's talk about that briefly as to why that's the case. The methyl shift is an intramolecular event. So the molecule is hot, it's a carbocation, it's unstable, it wants to stabilize. If it does that intramolecular methyl shift, it stabilizes itself. It doesn't have to wait for any prince to come and rescue it, right? It can self-stabilize. If the secondary carbocation, for it to form this compound, has to wait for a water molecule to find it in the correct orientation to gobble up that proton and give rise to that product. So that requires then collision between the carbocation and the water molecule. That takes time. But if the substrate, if the carbocation can simply move one group within the molecule to another position, that happens in a blink of an eye. So intramolecular events are always much, much faster than intermolecular events. So the time scale for a methyl or hydride shift is femtoseconds. The time scale for a water molecule to find a carbocation is literally thousands or tens of thousands of times longer. So long before a water molecule finds this, in fact, I would hazard, if you had 1,000 of these things, 950 of them would rearrange, right, before a water molecule found them. So it means then, because the major pathway involves the rearrangement, then the major products will stem from this carbocation, not from that one. Which is why the tetrasubstituted product is the major one, the disubstituted one is the minor, and this, it's intermediate, and then this one is minor. Okay, so this is interesting then because it creates a slightly peculiar nuance for organic chemists, which of course you are responsible for. So if we go back to the scenario where I say, I'm going to give you this alcohol, and I want you to generate this compound. I want you to make this alkene. Well, you know, if I simply add sulfuric acid and heat, yeah, I'll get this alkene, but my yield would be what, 3, 4, 5%? And that's not practical. That's the kind of stuff you get fired for. But if that's a compound they want you to make, you can't use the alcohol as the substrate, because any attempt to dehydrate this alcohol is going to generate the carbocation, the carbocations will rearrange, and therefore you're not going to get the compound you want. So what I'm going to do is not go E1. Instead, I'm going to convert the alcohol to a substrate which I know will give me E2 chemistry. So I will convert the alcohol into the bromo compound and then heat that under classic E2 conditions, 3 molar methoxide in methanol, right, and heat it, classic E2. And all you have to do is figure out how to go from the alcohol to the haloalkane, and that's very easy. There is a slew of what are called brominating agents, and those include things like PBr3, phosphorus tribromide, PBr5, there's SOBr2, and a whole bunch of others. So I would convert the alcohol to the bromoalkane. That is going to allow me to carry out E2 chemistry, and simply saying, here's the Br, here's the H, that's what I'm going to get chemistry. So as a rule of thumb, we want to try to avoid carbocations, because carbocations can rearrange, and if they can rearrange, the rule of thumb is that they will rearrange. Alright, beyond that rearrangement, there is another peculiar one, which is related, which tends to happen with alcohols and carbocations. So let's say I had, I'm just going to leave that for you guys to look at it again, give it 5 more seconds, and I'm going to erase it. Or you can pause the tape. Okay, so I'm going to erase it. Let's do another example. Let's say I give you this compound. And we said we wanted to dehydrate this compound. Well, then why do we look at this one? So what would happen, let's say the question is, draw the products from the dehydration of this compound. And I won't give you a question that open-ended. That's a bit, there are a lot of products, as you'll see in a second. Well, what do we do? Well, I know it's an acid. Acids do one thing and one thing only. They protonate. They protonate bases, which means lone pairs or pi pairs. So the alcohol attacks the acid. This is going to be an acid-base reaction. Therefore, it's in equilibrium. I'm going to lose X minus, and that will generate the corresponding oxonium ion. Now this time, I can actually lose the water molecule on its own because secondary carbocations are modestly stable. So I'm going to lose the water molecule that is also an equilibrium. Loss of water from an oxonium ion is an equilibrium. And that will generate the secondary carbocation. The secondary carbocation will rearrange. It can go from secondary to tertiary. So I can have a methyl shift, and that will generate this species, which is a tertiary carbocation. This is secondary, this is a tertiary carbocation. That tertiary carbocation can rearrange in several ways. One, for example, is I can do a hydride shift, because there's an H in this position. So I can do a hydride shift. Right? I'll draw that one, and that's going to give me another tertiary carbocation. Okay? Or I can do something completely different. Now remember, this p orbital that's in that position is actually leaning over and sampling groups in adjacent carbon. It could have leaned over and borrowed the H from here, right? So I could have done another type of hydride shift. Let's use a different color. So let's say there's an H here. I can do a hydride shift this way, another hydride shift, and that's going to generate this product, this carbocation. another tertiary carbocation. And that will happen. But what is even more interesting is that, so this p orbital is sampling electron pairs on the adjacent atom, on the adjacent carbon. So it's sampling the CH, but in this carbon, in addition to CH, there are also CCs, and they also have electrons. And there is no earthly reason why this, I'm just going to erase these, there's no earthly reason why I'm limited to doing a CH. And I know that because we did methyl shifts before. So I could actually have the p orbital steal 2 electrons from the carbon-carbon bond and generate this species. Now, it's a really good idea when you're doing these, particularly when they involve rearrangements, to number your carbons. That way you leave a paper trail as to what is happening. So if I go all the way back here and I number this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, so I'm still 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we moved carbon 4 to carbon 2. So I'm going to have 1, 2, 4, 3, 5, 6, 7, 8, 9, 10. What I did is I dissolved the 6-10 bond, and I used those 2 electrons to zip together 10 and 3. So I'm going to move the 2 electrons from the 6-10 bond and make a 10-3 bond. But in the process, 6 loses the electron it invested in the 6-10 bond. So 6 ends up without an electron, hence positively charged. So I'm going to end up with 1, 2, 4, 3, 5, 6, 7, 8, 9, 10. And 6 has a positive charge. Well, what I've also done is I've gone from a 5-membered ring, and I've now incorporated carbon 3, which now means it's a 6-membered ring, right? So I can really redraw that species like this. Right? I can redraw that species like this. So it's carbon 1, 2, 4, 3, 5, 6, 7, 8, 9, and 10. And 6 has a positive charge. Now that's a secondary carbocation. I could have that secondary carbocation rearrange. I can do a hydride shift between 7 and 6. Another hydride shift between 8 and 7. Then between 9 and 8, and 10 and 9, and so on. And I can do a methyl shift from 5 to 6. Right? I can do a methyl shift from 5 to 6, and that's going to generate this carbocation. Right? Which is tertiary. And then from here, I can do a hydride shift to generate the carbocation off the ring. So here's my point. And I didn't even do all of them. My point is, once you set loose a carbocation, you've opened Pandora's box to possibilities. Because any arrangement, any rearrangement that is possible, which involves anything secondary, anything tertiary, they'll all happen. And you've lost control, which is why we say, if you have a choice of E1 or E2, do E2. If you have a choice of SN1 or SN2, do SN2. Because you want to circumvent carbocation formation. Because carbocations are hot reactive species. They will find a way to self-stabilize. And once you've opened the door, unless you've really constrained the conditions, which you can do, once you've opened the door to make a carbocation, all bets are off, and all hell breaks loose. And here's the trick. Water then can come as a base and pluck off a proton from any of those carbocations. So you can imagine if I made this carbocation, before it rearranges, because secondaries are modestly stable, I can pluck off a proton from here and make a double bond. When it rearranges, I can pluck a proton off from here, double bond here, from there, double bond here, from here, double bond here. If it rearranges here, take a proton from here, but a double bond, proton from here, make a double bond. If it went to this one, double bond, double bond. If it goes to this one, I can make a double bond here. When I rearrange, double bond here, double bond here, double bond here. And the problem is they're all isomers, which means their boiling points are going to be very, very similar. Their melting points, very, very similar. In an attempt to separate one of those from 15 others very much like it, I mean, you're basically screwed. So you want to avoid carbocation formation. So I will never ask you, draw all the products of the reaction, because that'll take you the entire exam. I might ask you to show me how a particular one forms. So for example, I might ask you to show me how you go from this compound to this compound. That is probably the more typical question. How do I go from that compound to this one? And the answer is, you protonate the OH, water leaves, you do a rearrangement, you do this process, which we're going to come back to in a second, right? It's called a ring expansion. It's called a ring expansion. You do a ring expansion, then there's another methyl shift, and then you lose a proton from this carbon. So water molecule, the same one lost here, comes in, acts as a base, plucks off the proton, and you end up with your corresponding product. And that's how you make that one. Okay, just a quick point. So this process in which we go from a smaller ring, a 5-membered ring, to a larger ring, a 6-membered ring, is called a ring expansion. The question you would ask is, well look, prior to the ring expansion, I had a tertiary carbocation. Am I in any way bothered that I went from a tertiary carbocation to a secondary one? And the answer is no. Because any rearrangement helps to stabilize the species in the sense that in the process of going from tertiary to secondary, at some point, the plus charge was delocalized between the two atoms involved. But in the particular case of ring expansion, there's something even better. 5-membered rings still have ring strain because they've got a small amount of angle strain and a modest amount of torsional strain. 6-membered rings are completely devoid of ring strain. So in the rearrangement from 5-membered ring to 6-membered ring, I release ring strain. And so really it is to the system's advantage to do a ring expansion. So really, when this carbocation is confronted with a myriad of possibilities, I would say 80% of them will go via the ring expansion, right? Because that is a significant release of strain, significant stabilization. Okay, so we can so we can prepare alkenes then by dehydration of alcohols. So far we've seen preparation of alkenes by elimination. We did elimination of hydrogen halides and alcohols, and water. And then the third one, so this is, I think I was doing ABC. So C would be dehalogenation. So if I take a, let's use the diagram. If I take a Vic or Vicinal dibromide, and it also works with diiodides, and I treat them with sodium iodide in acetone, that will generate, let's make it a little bit simpler, that will generate the corresponding alkene. The reaction works with both Vic dibromides and Vic diiodides. Now, by the way, they're called Vic because the two bromines, the dibromide, they're on adjacent carbons. They're on carbons in the same vicinity. So they're called Vic dibromides. That is to be distinguished from species like these, which are called GEM, which is short for geminal dibromides. Right? And the term Vic and GEM, so GEM means twin. So in other words, they're born from the same parent carbon. And it's not limited to dibromides. I can have Vic dimethyl, I can have Vic dihydroxy, and so on and so on. So I can have gem dimethyl, gem dichloro, it doesn't really matter. So gem just means I've got like species on the same carbon. Vic or vicinal means I've got like species on adjacent carbons, on carbons in the same vicinity. If I treat Vic dibromides or Vic diiodides with sodium iodide and acetone, that gives me what essentially is an E2 reaction to give rise to the alkene. The reaction is kind of interesting because the iodide carries out, as I said, what is fundamentally an E2 reaction. And if I were to finish this out, what you end up getting is IBr plus Br minus. So if I treat the Vic dibromide with sodium iodide and acetone, the I minus, as far as it's concerned, functions as a nucleophile. And it attacks the Br, and we'll get that in a second. But if you were to ask the organic compound, hey, what happened to you? It would say, man, I underwent an E2 reaction. Right? Because if you look at the curved arrows, that is the classic E2. So if you ask the organic what happened to you, it'll say I underwent an E2. If you ask the iodide what did you do, it'll say I acted as a nucleophile. Right? It didn't act as a base, it acted as a nucleophile. So the iodide goes after the bromine. Now, 2 points. Point 1. Why would iodide attack a Br when the iodide is a nucleophile? That's question 1. Question 2. Why is the reaction limited to Vic dibromides and Vic diiodides? Why not the dichlorides? And then there's a little nuance at the end, which is, we'll talk about interhalogens in a second. So here's the kicker. If I looked at this without thinking too hard, I might say, well, this is impossible, because this Br has a delta minus charge. And 2 electron-rich things should not attack each other. That should not be happening. But here's the trick. Br is a big atom. Right? The Br is a very large atom. And as a result, Br is very polarizable. In other words, the electrons in the Br atom are so far from the nucleus that they're held very, very loosely. So as the I minus, right, as the I minus swims along very innocently, the negative charge in the I starts to distort the electron cloud around in this bromine. So as the I minus approaches and these electrons are held loosely, they actually distort. So what you see is this. The electron cloud distorts in that fashion. And that then creates a delta plus on that side and a delta minus on that side. So of course the iodide, recognizing a delta plus charge, targets and goes in. And the closer it gets, the greater the distortion gets. And as the distortion gets larger, this electron density in the Br starts to leak into this position, and I kick out the Br minus. Which explains why the reaction only happens with Br and I. Because Br and I are big. So if it was iodine, that's the size of the diiodide. So those electrons are even more loosely held, they're more polarizable. But if it were a chloride, well, those electrons, these valence electrons, are much more tightly held. They will not succumb to the approach of the iodine, because these are held more tightly. They will not distort. So bigger atoms are more polarizable. We talked about this when we looked at van der Waals interactions, right? So larger atoms are more polarizable, and as a result, they will distort more readily. So Br is the threshold, that's the magic size. So the dibromide and the diiodides work. There's one little corollary to that. As the size drops from iodine to bromine to chlorine to fluorine, the electronegativity rises. So if it were the diiodide, there's only a delta minus charge. If it's a dibromide, there would be a delta minus minus charge. By the time you get to dichloride, it's delta minus minus minus. So the I minus probably won't even sniff around the delta minus minus minus. The repulsion is greater. right? But it's a more inviting arrangement when it's a diiodide or the dibromide. Right, so we answered 2 questions. The last point is a little bit of a nuance here. Compounds like these are called interhalogens. And they're interesting, and those of you who are chemistry majors, you'll study this in advanced inorganic chemistry. But what is also interesting is that it doesn't stay that way. The iodide attacks the interhalogen, and what you end up getting is I2 and Br minus. And then the I2 colors the solution sort of violet. So you can tell this reaction is going because you end up with a sort of a violet brownish sort of color in the reaction. Okay, so we've looked at 3 methods of preparing alkenes. One was from elimination of hydrogen halides. One was dehydration, which is interesting because it involves rearrangements. And the third is dehalogenation, which is unique to Vic dibromides and Vic diiodides. So at that point, we'll stop this lecture and we'll pick up the next lecture in a few minutes.